Play. 7-5, day 1. Oh, shut up. There's a little bit new here. Okay, we have to know what an equilibriant force is before we can get started.
When they're equal.
Oh, Mr. Barron did teach you something.
No,
What's
actually,
equal?
That was equilibrium from physics. So, yeah.
Equilibriant force.
You know there's two different types of pneumonia.
Yes, bacterial and viral.
Why isn't it? I got embarrassed.
Why do we need to know?
Equilibriant force is the counterbalance to the resultant vector. So it is the opposite of the resultant vector. So it has the same magnitude as the resultant, but it's going in the opposite direction. Counterbalance. It's like tug of war. When both sides are, neither side's moving, you've got opposite vectors there. The equilibriant counterbalances the resultant.
That's when you let go and they all fall.
Yeah. So it's the opposite of the resultant.
So it's a negative resultant?
So it will have the same magnitude but the opposite direction as the resultant. Same magnitude, opposite direction. So a picture of what this might look like. Here's our big old box that's sitting on the ground, whatever it is. We've got two ropes pulling on it. Force 1 and force 2, however big they are, whatever angle's in between them. If I wanted to see the result of those two forces working together, I need to add them together, so what would I have to do? Head to tail. So if I slide one of them, it doesn't matter which one. I like this one. It's easier for me to draw this way. So if I slide force 1 down here, the resultant now is this vector right here. Could you now draw in the equilibriant vector? What would it look like?
It would go from the top of F1.
It would not. I need a green. Give me a... Where am I? Oh, I put my green.
It goes from the bottom of F2.
It goes right from here where the box is at. Because it's not adding anything together. It's just the opposite of R. So if R was pulling to the right, just goes the opposite way and the same, about the same length. You know, it has to have the same magnitude. So I'm going to try to draw it so it's the same length.
What? I didn't know that I had
Equilibriant. It's the opposite of the resultant. Opposite vectors go in opposite directions, but they have the exact same magnitude.
Why do I take notes?
What do you mean? You're running off your paper? Did you not see me move to the center here?
No.
Do as I do. Do as I do and you can't get in trouble. Gosh.
It's do as you say, not as you do.
Well, do as I do, not as I say, because I don't always say things right. Do as I...
I'm learning the hard way.
Yes. I usually do everything okay. I don't always say it. All right, are we good now? Is everybody happy? Got their picture back on their paper? Okay, I'll just write this first one out and then we'll wait for everybody to catch up. We've got two forces acting on a point. Force 1 has 128 pounds of force. Force 2, 253 pounds. The equilibriant force is 320 pounds. Can you find the angle between force 1 and force 2?
My hand doesn't work. Cannot be.
Okay, I'll let you write that down. Are we good?
No.
Jamie's still bobbing her head up and down too.
I want to apologize to you. I'm not.
She's not the only one.
Apology shows weakness. Weakness not shown.
York's got the old head bob going on too. He's good. Augusto, you good yet? Okay. Because I like it. Okay, here we go. So, because they give me this piece of information about the equilibriant force, what other vector do I know something about? The resultant. What do I know about the resultant force?
320.
It's 320 also. Remember, because equilibriant and resultant have the same magnitude, they're just going in opposite directions. So because they tell me this, I know the resultant is also 320 pounds. So,
So are we using side?
go to the middle of your paper,
In the middle.
Thank you. I appreciate it.
okay, to have your point. We've got two forces pulling on this point. I don't know what the angle between them is, that's my goal. So force 1 is 128. Force 2 is 253. Our goal is to find this angle between them. How wide are those two ropes that are pulling on that point? Okay, so what I want to do is add these two vectors together so that I can get my resultant into the picture, because I know something about the resultant. So what do I have to do to show the resultant? Slide them head to tail. I'm going to slide the 128 down to the arrowhead here. Here's my resultant.
And now we know side, side, side.
Very good. This side is 320. We now know side, side, side. I agree. When you run side, 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 you're obviously going to get three angle measures back inside of this triangle. I'm going to write all three of them in, and then you're going to tell me how we're going to answer the question after that. Austin? Because none of those angles actually answer the question.
Well, yep.
Okay.
We have to do it for both triangles.
Nope. Well, you could.
Do one
There's an easier way.
minus the other one and then
This shortcut shows.
Okay. Yeah, there's a couple ways to get there.
the easier way. A better one.
Okay, so tell me what the three angles are when you get them.
Angles
I want, let's see, the biggest one's going to be across from the 320, so what's this one?
109.
109.
101. It's actually 118.
Oh.
Okay,
It's
that's
actually
fine.
one.
110.
Kenley, I think you're wrong.
Yeah, 110.
We're just, because we're arguing between 109 and 110 at this
It's
point.
110.
It's,
Yeah,
109.8.
all right, 110.
What?
Try your side, side, side again. Are you might want to check your mode. You're probably in radian mode
Oh,
because you're factory set there.
I'm not.
Oh, good call.
That's not my problem.
Nope, you didn't type in the right three numbers.
I have more problems than you can help me with. I have to figure it out.
22.
Okay, let's see. The small angle over here is how much? The smallest?
22.
22. And then the middle angle?
48.
48. Okay, like I said, none of those answers the question of what was this original angle between here.
What did they do with the
But what did we do yesterday? Remember, this is a parallelogram.
transversal something? 180.
So would it be 22 plus 48?
Or it would be 180 minus the 110, because remember, the angle I want and this 110 are part of a parallelogram.
Could you do it either way, though?
I can,
Okay.
because I can transfer the 48 over because of alternate interior. Do you like that better?
Yeah.
And then you just add those two together.
Yeah.
Or it's 180 minus the 110 because of the consecutive angles in a parallelogram.
Either way, it's 70.
Either way, it's going to be 70. So I don't know which way you want to wrap your brain around.
I'm confused.
Okay?
Can I download somebody else's program?
Mm-hmm. Yours is no good? Oh. We'll get you a good one here in a second. All right, what part are you confused on, Lexi?
How did you get 48?
Oh, I used alternate interior to transfer the 48 over because of the parallel lines and the transversal.
Oh, so then you just add 48 plus 22?
Yep.
Find that angle
Mhm.
you wanted.
So 70 degrees was the angle between the ropes to start with. Or Kenley's suggestion was, you've got the same triangle up here. So that's the angle across from the 253, and then you can add them together.
Well, I was close, I had 20 degrees, but...
Okay, we will get to a working program here in a minute. Okay, you're good with that one.
Are we done?
Why is it what?
Can you put that back?
Oh, I wrote it down wrong.
Can you put it back, please?
What do we get out of that?
Maybe that was the problem. She put 250. Oh, never mind, never mind.
Much sorry.
Just like Look, it says keep calm and carry on.
All right. Incline problems. These are right out of physics.
Joy.
Not an example yet. We got to have a little introduction. Make sure you have this on your note card too, because there will be an incline problem on the. Nope. Little picture. So we're on some kind of an incline, a ramp or a hill, something. So our hill will have an angle of inclination. Maybe you're pushing a wheelchair up a ramp, or maybe you're pushing a car up a hill. Hopefully that's not the case. But there's going to be something with some weight on this incline. Whatever it might be, has some weight to it. All right, so there's some physics going on here. I don't quite understand all the physics. A couple forces going. One force that you can understand is gravity, pulling that weight straight down to the center of the earth. So here's the force, gravity force.
Negative 9.8.
Okay? Then there's some friction force. Friction force comes in this way. And like I said, I don't quite get all the physics here. I just understand the triangle and the math. Actually, no, this is the friction force here. This one. So these two are added together head to tail, and this will always make a right angle over here.
Nope. I didn't get it.
Just draw that triangle.
Mine doesn't look like that.
Okay, and know that the weight of the box is this one here pulling straight down. Just go with it, because I don't understand the physics either, I just know the math. Okay? This one here, this one that I drew here, is parallel to the hill. So there's a little parallel to the hill business going on here. And they call this vector represents the force needed to keep W on the hill, so that it's not going to slide backwards and it's not going to move forward. It's just the amount of force needed to hold it steady. You would have to overcome this force to actually push it up the hill. So this is the force needed to keep W on the hill. That's this one right here. And then there's some similar triangle business going on, and the angle at the top of this triangle is equal to the angle of the hill. So this theta here transfers here.
Is this for every single problem?
Every single incline problem has this same triangle going on. Who proved all that? I have no idea.
You mean the angle like that's coming down from
Of the hill, yep, whatever angle the hill is at, that's the angle in this right triangle also. Always. Your incline problems will always have this right triangle going on underneath.
Obviously, we're gonna have to use the angle on the side.
So, are you ready for an incline problem? One. Example 2. Find the force needed to keep a 3,200-pound car parked on a 15-degree hill. So incline problems, always the same picture. You got your car on the hill. So here's the hill. It's a 15-degree hill. And here's my car. You don't have to draw a car, you can put a little box if you want. A little handle, a little
clown car?
Yep, clown car.
It looks like the car can pull down.
There it is.
Oh, that's a motorhome. It's got a door.
Okay, now can you draw the right triangle underneath that with the physics going on?
I'm not even done drawing my car.
Oh, okay, I'll wait a little bit.
I drew a bus.
So we want to know how much force is needed to keep it on the hill. Well, the two forces working are gravity pulling straight down, added to the force needed to keep it on the hill, which is parallel to the hill, and then the other side makes the right angle. Every time.
Yeah, definitely not my best piece of art.
Right angle's there every time. Okay, so besides the right angle, what other two parts of that triangle do I know?
The angle,
The angle at the top is 15 degrees. And
the bottom is parallel.
bottom's parallel, and that bottom one is the one I'm looking for.
And the other angle is 75 degrees.
Okay, if I want that, but I don't want that, what else do I know?
Can I write that down?
The left
You
side
can.
triangle is, never mind.
The hypotenuse of this triangle is the weight of the car. Remember I said the weight pull, whatever the weight is, that's what goes on this straight down vector. So 3,200. And all we want is the force needed to keep it on the hill. That's the one parallel to the hill down here. So we do have angle, side.
Wait, how come that's 15?
Because that's what the hill was. Whatever the hill is, it transfers into the triangle. Whatever the hill is, it transfers into the triangle.
I should probably write that down.
Yep. So run your angle, side.
Wait, is
When I come down and go over,
This, what are you asking?
you go down,
Down,
and go over.
then you go over.
Do we need an arrow going back up?
This is actually the resultant is right here, so,
Arrow going down?
yep, arrow going down. This is the resultant vector of these two forces. What is the answer, Austin? 2 sig figs they're going to give you on these when you look them up in the book. Yep.
so then that would be 800.
840, you said? 830.
Yeah.
So if the brakes gave out on the car, you'd need a couple people to be able to hold 830 pounds. It's not 830?
Yes, it is.
800, well, I got 828.
2 sig figs. 2 sig figs.
That would be -2 for us.
Minus 2 for you.
Stop that.
Now are we in agreement?
Yeah.
Yeah.
Okay.
We done?
I have 2 left. Oh. Example 3. 2 tugboats are pulling in a disabled speedboat. So 2
I don't think you need 2 tugboats for one speedboat.
tugs. Maybe it's a nice, great, big yacht kind of speedboat. 2 tugs
But yeah.
Yeah.
pulling,
Sorry.
We don't mean to burst your bubble.
pulling a cruise ship. How's that?
Oh, pulling a killer whale.
Cruise ship. I don't even know if I spelled that right.
Ship. Yep. That was right.
Force 1 can pull 1,280 pounds, with force 2, 1,420 pounds. They're going to keep the angle between them at 28.2 degrees. That's pretty close together. Can you find the magnitude and direction of the equilibriant force?
Okay. You need to try for
I will.
That's all fine.
Okay. And I'm going to tell you what they mean by direction. What can't you? Oh, you're way up there?
Yeah.
Oh, what do you do? Wait till I'm all done?
No.
LH, do you wait till I'm all done?
Well, your hand is kind of in the way for like half the time.
I'm talking though.
Yeah, but you have
But
to
then
fast.
sometimes you write down different stuff.
Oh, knock it off. I do not.
You,
That is true.
I just write less than what I'm saying.
yeah, we wrote disabled, but
Yeah. It's not necessary to the problem.
So why did you say it?
So you can have a vision. It's all about vision in math, so I can draw a nice picture.
There were some shots fired, Matt Casey. Stop doing that.
Shots were fired.
No, they weren't. I would have hurt them.
You're sad, you did.
Everyone's really uptight today.
Getting close to Christmas, everybody's getting uptight. Are we ready? Lexi, you ready? Okay.
Stop throwing me under the
Okay, LH, are you ready?
bus. Stop.
Then they might know.
Please.
Let's go.
Move to the middle of your paper. Okay, here's our disabled cruise ship. And then here's our 2 tugboats. 1280. They're fairly close together.
Well, that's 1280 now, 128. I was gonna say.
1420 and a 28.2 degree angle between them. The question being asked is everything about the equilibriant, but we know there's a direct relation from equilibriant back to which vector?
our
Resultant vector. So we're going to slide these so we can draw in our resultant vector. So we'll slide one of them. I like this one because I know how to put my hand over the picture. Yes. So here's my resultant. And everything is being asked about the equilibriant. So I will draw in the equilibriant. Which way is the equilibriant going to go?
The opposite way.
Opposite way. Equilibriant. Okay, we've got a nice triangle here, but I only know the 2 sides. What else can I find so that we can run a program?
180 minus 28.
Yes, because of the parallelogram thing, this angle and the consecutive one are supplementary, so 180
151.8.
So now you're going to run SAS. And you're going to tell me the other side and the two angles. Well, your SAS doesn't work. Or
No.
side, side, side doesn't work.
No, it does. I just.
Oh, you did it wrong? You got a good working side, side, side now?
The only one that's messed up is, no, it's not.
Oh,
No. Side, you gotta help me with that.
okay.
I got SAS, that's right.
All right, what is our resultant? We're looking at 3 sig figs on the force.
2,620.
2620. Are we in agreement?
I guess so.
To 3 sig figs? Okay, give me the, let's see, this would be the small angle. Give me the small angle.
13.4.
13.4, because it's across from the small side.
Oh, okay, we're looking at that.
Yep. You're looking at the program, and then the big, what's the other bigger angle? You might as well give me that too. 14.8. Okay, so the question said, find the magnitude of the equilibriant force. How much force does this equilibriant have? 2620. Well, no, they don't do the negative business. Now the direction. What do they mean by direction? They don't mean the actual direction, because I have no idea which way these boats are actually going in the water. So what they want you to give is the, and I wish they'd say it better in the book, and they don't. They want to know the angle between the equilibriant and either force 1. You can give me this angle, or what's the angle between the equilibriant and force 2. One or the other is what they're looking for.
Oh, that's really easy.
So how do I get one of those angles?
180 minus the inside angle, right?
Yeah, if we go with this one, if we go with the 13.4, the angle I'm looking for just makes a linear pair with it, through the straight line. So 180 minus the 13.4. That's for the bottom one.
I thought you said that 28.2 will never be cut in half.
It wasn't. 13.4 is not half of 28.2.
Oh. Well, I mean,
I'm using the 13.4 that you gave me off of the program.
yeah.
So you can say the equilibriant is making what angle with force 2?
It's 166.
166.6 degrees with force 2.
Where did the 26
2620 off of the program. After you ran SAS, that was the missing side. Did you run your, and 3 sig figs.
okay.
Got it? Yep, 3 sig figs. Austin.
So it's force 2 because of,
That's the way they labeled force, the 1420.
okay, yeah.
All right, Michaela, you want me to explain where this is coming from again? Okay. First of all, just knowing, for direction, they're looking for the angle between the equilibriant and either force 2, which is this angle here, it's how far apart those are, or you can give me the angle between the equilibriant and force 1. Either one of those answers this question. So, I know that the equilibriant and the resultant make a straight line. I knew this angle here was 13.4 degrees, so I just needed the supplement to get all the way over to here. Good with that one?
Are you gonna do the top one?
Do you want to do the top one? What do I have to do? What's the top angle here going to be? 14.8. You don't have to give both on the homework. So you go 180 minus 14.8.
Okay, and that,
And that would be the angle between the equilibriant and force 1.
okay, so what is that in our little question thing that?
That's the direction.
What's the magnitude?
Magnitude is 2,620 pounds. Direction is one of those two angles. You can give either one. Doesn't matter. $26.20. Okay, last one. About as much as that one, maybe a little less. Okay, here we go. Example 4. 3 forces acting on a point. So this time we've got 3 ropes pulling. They are in equilibrium. How they expect you to do these on your own is beyond me. 'Cause the 3 forces are 980 pounds. Force 2, 760 pounds. And force 3 is 1,220 pounds. Can you find the angles between the forces? So this is kind of like a tug of war with 3 ropes, and no one's winning. That's what that means to be in equilibrium. Everything's pulling, and nothing's happening. So do you have a vision on that? Okay, I'll let you write that down. Everybody says no. I don't see that. To be in equilibrium means nothing's happening. Everything's just still. So, in the middle of your paper, come down a little bit. We've got 3 forces pulling. I don't know the angles between them. That's my goal. Got a 760. I got a 980. And I got a 1220. And our goal is to find all 3 angles between these ropes. So I'll say X degrees, Y degrees, Z degrees. That's our goal. Okay, if you think about this, this is where I'm like, how would you even know how to do this all on your own? What the heck?
Hey, how's it going?
What do you need?
Here's a question.
What do you got?
Can you help me find an angle?
Not right now. I got to finish up before we end. Give me like 3 minutes.
Okay, I'll go there.
Okay. Okay. So what it's saying, what I need you to see that you probably wouldn't have is that these 2 forces are working, because these 2 are the smaller forces, it's taking the 2 weak ones to counterbalance the strongest one. You don't get that? That's kind of a common sense thing. To know that if I've got 3 ropes, I don't know how else to say that. Because it's 3 ropes pulling, and these 2 weaker ones have to counterbalance the big giant.
Oh, okay.
That's what's happening here. Would you have been able to figure that out all on your own?
No.
No. So what this is actually giving me is the equilibriant force counteracting these 2 together.
So the biggest one would be
The biggest ones counterbalancing the 2 weaklings.
but like, the bigger one would be the equilibrium.
Always.
Always.
Yep, that's the only way that can work. And that's like kind of the common sense thing that I don't think anybody would have come up with on their own without me telling you. So I don't think it's a fair problem to just throw at you without any explanation here. So we slide the 760.
Yeah, the picture's a little off, but that's okay.
Yeah, it might be a little bit off. Oh yeah, I'm a little bit off. Because those are supposed to be in a line. Let's see, can I fix it? I'll just bend my line a little bit. The equilibriant and the resultant is supposed to be straight. So it's a little off.
I think we're all right.
But what do I know about the resultant?
Mine is actually not that bad.
1220.
It's 1220. So you are going to find these 3 angles in here. 1, 2, and 3. And you should be able to figure out that X, Y, and Z that we started with. I'm going to let you finish that one up for homework. I'm going to give you a couple more to try. Austin.
What's this one?
So,
Seriously.
like, if you find the angles for 1, 3, and 2,
Yes, 1, 3 to 9, right?
what
No.
122 do?
What?
So, 1, 2. Oh, just hitting it Okay.
Okay, and you should be able to get X, Y, and Z without too much trouble. I really think you can do it.
290 for now. I need to know.
6 and 8. And there's 5 easier ones for you to try for homework.
Okay, when you get that first angle,
Are we supposed to figure that out?
You are.